All right, hello, good morning. Welcome back to another Tuesday deep dive stream here with me, Tim. If you do not know, I am Tim. I go by Foamy Guy on GitHub and Discord. I stream around this time each week, 10 a.m. Central Time here on the Adafruit channel, working on stuff related to CircuitPython. If you don't know what CircuitPython is, this is basically a version of Python that is designed to run on tiny computers called microcontrollers. Typically, the way it works, when you use CircuitPython with these devices, you'll plug them into your computer with a USB cable. They will usually have a little USB plug there for you. Plug it into your computer with a USB cable. It shows up like a thumb drive, a mass storage volume. You can then edit a Python code file on that drive. When you save it, the microcontroller will interpret and execute the Python code for you. And your code can interact with whatever other electronical and hardware peripherals you hook up to your microcontroller. So some devices are very general, like these Raspberry Pi Picos, don't really have a lot built in. Other devices are more purpose-built. They have much more built in, like these playgrounds have a bunch of LEDs and a bunch of other sensors and alligator clips for hooking up even more stuff, and a speaker and a IR input and output on this one. So lots of different devices with different shapes and sizes, different capabilities. But you can write Python code to interface with all of those different capabilities. If you would like to learn more about the project, CircuitPython.org is a good place to do so. Also, you can join us on the Discord, which is linked down below on the screen there. As always, we will say thanks to Adafruit. Adafruit is a hardware and software company based out of New York that makes CircuitPython possible by paying a team of folks to work on it, submit code, review PRs, do all of this sort of stuff, maintenance, all kinds of things. So if you would like to help support CircuitPython, as well as the other open source work that Adafruit pays people to do, there's Arduino drivers and other things that are totally outside the CircuitPython world, but Adafruit does still pay people to work on them and then publish the code under permissive open source licenses. So if you would like to help support that, one of the easiest ways to do it is by purchasing hardware from them, which you can do on the website there at adafruit.com. And if you check back later today, 4 p.m. Eastern, 1 p.m. Pacific, you will find JP's product pick of the week, where you can not only help support the open source cause by buying products from Adafruit, you can do so at a wonderfully amazing discount for whatever the product happens to be this week. So I am diving in today. Not really diving in, I'm staying in, because this is what I've been doing before the stream started as well. But what I'm working on is reviewing, I want the camera there, but it keeps giving me the wrong screen. I am reviewing the changes for supporting the Teenage Engineering SP-1 device in CircuitPython, which is this device right here. This is like a little unreleased stem player, they call it, which was not a term that I was familiar with previously, but I have come to understand that it is kind of like a term in the audio world, in the music world. So stem, as far as I understand it, is like a multi-track song. So you can have a stem of a song, and it would contain, you know, like maybe the drums on one track and the guitar on one track and the vocals on one track and maybe the bass or whatever on another track. And so this is a relatively common thing, as it turns out. And this stem player here is designed to play that type of audio, and in particular 4 tracks like this, like I just mentioned. And the main sort of hardware functionality gimmick of the device, the main thing it does is it's got these little faders here. There's 4 of them, and it's got 4 buttons here. And with your 4-track audio, you can then use the faders to control the levels that each of those 4 tracks are mixed. So if you just leave one of them up, then you can hear that single track by itself. If you put 2 of them up, you can hear 2 of them together. If you have all 4 of them up, then you hear the whole song. If you want to like back down the vocals or whatever, but still hear them, then you can lower one to halfway or whatever is needed for your song. So this device is made by Teenage Engineering, but it was not actually released through proper channels. So this was like a sort of a crossover thing, a branding partnership thing that fell apart, and these devices ended up going, like, not being sold directly to general consumers and stuff, but instead they kind of got held up for a few years. As I understand it, maybe they went through some kind of bankruptcy filing and that sort of thing, and eventually they're kind of being liquidated by this company whose name escapes me off the top of my head. If you search Teenage Engineering SP-1 online, you'll find the place that still has these in the States. I think there may be a couple of different suppliers in Europe as well that have some of these too. I think I've seen people talking about on the Discord, but I'm less sure on that front. So it's a couple years old at this point, and supplies presumably are limited. I have no idea how many of these things they made, but they are available in this sort of like secondhand liquidation sort of market where they're quite cheap compared to what they would have been originally, I imagine. But they come as is. There's like no instruction manual. There's no real support. Like it's not actually didn't actually become a real product. So if you buy it, it's a thing, and it kind of does what it was intended to do originally. But you're on your own as far as like if it doesn't work, that's on you. If it doesn't do what you want, that's on you. There's no real support for how to use it. There's a couple documents floating around that kind of made their way out into the world. So you can read up. There's a little bit of information out there, but it's not the full-on Teenage Engineering docs experience where they kind of lay out every single thing for you. This one is very much like got binned and became available, but yeah, like I said, it's kind of you're on your own sort of a deal with it. So I am working on adding CircuitPython support to it, which is coming along pretty nicely. And what I'm doing specifically right this moment is I am reviewing / cleaning up the changes in the CircuitPython core that were made in order to add support for this device. So there's a couple of different things going on with this device that required little bits and bobs of changes here and there in the core. At a high level, what they are is like the way the watchdog works. The watchdog gets armed by the bootloader, and CircuitPython, or whatever app comes after the bootloader, is responsible for feeding the watchdog. Otherwise, the device will reset. So there's new code in the core here that will feed the watchdog at appropriate times when other stuff is occurring, so that it won't just reset during a file write or a while true loop and that kind of stuff. So that's one of the things, the watchdog. Another thing was like a fix in analog IO, because all the buttons on this device actually, well, most of the buttons are actually hooked up to, what do they call that? Resistor ladder? Yeah. So they are read with an analog pin or a couple of analog pins instead of plain digital in out. So those buttons needed analog working. We ran into an issue while I was working on this with analog. So there's a fix in there for that. What else is there? So there's a couple other things. The eMMC support and auto mounting stuff. So this device has a 4 gigabyte eMMC chip. I think it's this big one here, if I recall correctly. Toshiba, is there a little light in there, or is that just reflection? Just reflection. For a second, I thought there was like a little LED down in there, but no. Anyway, though, so it's got this 4 gigs of eMMC storage, and so that is now hooked up. Originally, that was using, I think it's a custom format. I'm still a little unclear on if that's like a widely used thing. I don't think so. I believe it was a custom format to this device, but I'm still relatively new to audio stuff, so it's possible it's just like a higher end audio thing that I'm not familiar with. That's possible as well. I just don't know for sure. But what I have done with the eMMC instead of that custom format, and the way it worked, is put a file system on there. So it's FAT file system formatted, and it mounts to your computer as this 4 gigabyte volume. So when you have the device plugged in, you get CircuitPy like normal. You also get, which you might be familiar with if you use SD card devices these days, you get this extra volume, which in this case maps to the eMMC on the device, and you can load your songs right inside of here. So I have an Adafruit demo song, and then I have a couple other songs that I converted and used while I was testing. And so lots of this code is definitely vibed up, came straight out of the agent. And so I am going through removing huge prose comments that are more to do with like the timeline of while I was working on this and the development history and the and references to the plan docs and stuff like that. I'm removing comments like that and reviewing the code a little bit as well as I go, although I am going to probably still do another pass on the code. I'm looking mostly at comments right now and trying to just take inventory of what all the specific changes were, and then I will go back through, and there's a few changes I may be able to drop. So there is some stuff that I think is put in here sort of out of an abundance of caution. I need to look into whether it's actually strictly necessary or not, and maybe some of that stuff could come back out. But that is kind of where I'm at, is reviewing this agent output core change code to get it whipped into shape to actually be submittable. What is up, Liz? Good morning. Nice to see you, my friend. Let us see here. All right, so yeah, I think I left off around here. This one I kept, but I do have a note to myself on this one to go back and maybe review it. Here's the notes that I'm working on for eventually posting on the PR. Read next. Okay, bytes. The cards 512 is read only. Nothing a color. And reach changes what it says. I think we don't need anything except this. Yeah. So we get the signature. It's the name of the function. It returns bytes, and then it tells you what it returns. And it tells you that it's read-only. I think that's a good... I don't need anything else. So this is status. The card status register, R1 bits, 39 to 8 of the response. Handy at bring up. Nothing depends on it. So we definitely don't need that. That's not helpful. I think we could keep this part. Maybe it would fit up here fine, though. Let's see here. Usually go and nuke the M dashes. Profile 0. Reset profile. So it zeros the per block cycle accumulators. So a bench row measures only its own reads. Constructor calls it 2. I don't even know that we need this part of it as well, but we definitely don't need the others. Property. So this is, yeah, I don't think I mentioned the specific file we're in. If anyone is following along at home, this is the bindings for the eMMC object. Although I do think I'm going to move this. I put that in here, right? Did I do that? Move to shared bindings. Yeah, I want to move this to shared bindings, but I do want to go through and edit the comments and stuff first, and then what I'll do is I'll make a commit, like make a branch, get committed, and then I can check that branch out back in the agent sandbox and edit it from there. 16-byte CID. We don't need this. So this is talking about a phase of development, right? So it does, one of the things is like while you're developing with Claude Code, I've got all these plan files that are laying out how to do different bits and pieces of it, and it's always wanting to go in and sprinkle comments with like referring back to those plan files, which is not super helpful. VM at 3.9 is that, and PureV at 9. I think we don't even actually need anything else, because this is all talking about the acceptance values, and so it's talking about acceptance values of that phase of the plan. So it's saying like it wanted to read that register and get that result. And if it didn't, then it would have been considered not correct. But conceivably at some point in the future, this may be used for some other device, right? And then if it's a different manufacturer, maybe it has a different number or whatever, so it doesn't really need to comment what it was looking for on this device. The worst, although I will say this isn't currently at least this isn't a module that is specific to the device. There is some code that could maybe get split. There's kind of like half of it that could get split and moved out, but there is another half of it that's quite specific to this device, because the way it feeds the watchdog in between and the way that it hard codes the pins that are connected to the MC for auto mount. I mean, the worst start but haven't seen the session yet, so we don't need to keep any history of like what the worst was or what the best was. Write enabled whether this object may write at all, false on a default EMC, false on every object in a build without. So I think we don't need false. I think we can just say false by default, and like everything else is kind of goes without saying, right? You can set it to true to write. The other thing it was talking about there was a different build or whatever, because there was a build from before write was implemented, and in the plan it was like, ooh, we're not going to do write because that's dangerous. It could erase whatever's there. And so it was very careful to like not overwrite the stuff that was there, which was already empty anyway because I wiped it. But and so we did, I did all read first, and then once read was working, then I started working on write, and I went back and told it, hey, okay, I verified there's nothing important, we can write on this thing now. So, and then before that, there was like a build flag for compiling in the write. I'll have to check, actually. Let me make a note of that. To check if build flag for EMC, I'm just going to go with EMC, even though there's two M's. C is still in, and maybe remove, if so. I suspect we won't want that, but I'm not sure. Because I think kind of just the default should be, it can be writable or readable. Like when you mount, you get to choose, if I recall correctly, if you do it from code. If it auto mounts, then it's writable to the host, the PC. The worst, yeah, so it's another one. We don't need this. Microseconds, the card declares this. Number, I don't think we need this. Right, errors. CRC status tokens that were not 010. We don't need acceptance. High speed, true once HS timing is 0. Has been read back. So one thing is these are like properties. When I move this to shared bindings, if it can live over there, which I'm hoping it can, I'll probably rework the comments here to make them match the shared binding style of comments and docs, because that will then auto generate the doc strings. That's where those come from. False means the bus is at power on 6. So this eMMC can run at two different speeds. There's a 32 megahertz speed. There's a 16 megahertz speed. I did 16 first. Eventually, I went back and added 32. False means the bus is on at the power on 16. Yeah, we don't need weather. We don't need this afterwards. I don't think we even care about at the power on, just at 16. Yeah, we don't care how it got there, when it got there, just if it's false, it's on 16. Frequency, the SPIM data clock phase in hertz read out of the peripheral rather than remembered. Yeah, that's like it telling itself that we looked this up by looking at a register instead of, just finding this or whatever in wherever, datasheet or in memory. They're calling memory what they're able to regurgitate the text from. Profile, where a block's time actually goes in microseconds. Oh, get profile? Get profile. So this we might remove, actually. We are still in bindings. Remove this. So I believe this was mainly meant for testing the speed of reads and writes, to be able to compare a few different things. Like we were comparing 16 megahertz against 32 megahertz when I added in the support for the 32. We also did some comparison, the agent and I did some comparison when FAT was added, because originally it was this whole other format where it was parsing the audio data out of there. So this is talking about the test that determined basically whether 32 megahertz was actually worth it or not. Spoiler alert, it was. It made the both reading and writing a bit faster, which was really nice. But I think ultimately we may not need the whole function. I'm going to leave the comment and everything here because it adds context to what it is. But I think probably the whole thing can get deleted. And if it turns out that the whole thing can't get deleted, then I definitely will come back and remove the comment, though. Full diagnostic struct for the bring up. Maybe diagnostics also. I think that's another one where we can probably drop that, because this was just really mostly needed while I was developing and then while I was testing those different things, which is kind of a relief. This file got a bit bigger than I was thinking it would be. And those are kind of two of the largest chunks that could potentially get cut out, so that's actually nice. Module level diagnostics, and the auto mount flag. We're probably not going to need any of this, honestly. With the supervisor, oh, there's more diagnostics, actually. Add that to the list of maybe get rid ofs. Make this maybe remove, because I do need to double check that it's fine to remove, that it's only for measurement, diagnostics, profiling, stuff that is helpful during dev, but not like really useful to the end user. Yeah, that's the same thing. I'm going to leave the comment there because it adds context of what that is, but off the top of my head, I think that's probably getting removed. True when the card belongs to the supervisor's SD mount. Do we need an IE? IE when EMCC will refuse? Yeah, I don't know if that's really helpful. A tool can then say which of the two worlds it is in instead of guessing. A tool. Okay, I don't think this whole part we don't really need. This is just saying like something could read the Boolean and then decide based on that, which goes without saying. True. Yeah, I think we can just say true when the card belongs to the supervisor's SD mount, false otherwise. Okay. We got a couple things to come back through and prune, I think, from this file, but I need to make sure that they are okay to remove. Block dev is also in here. Block device face. We don't need to retain the plan number or anything. Dragging the rest of the module's headers the same shape. Native matters. Yeah, Claudism, native matters for blah blah blah, and it's not the blah 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 blah. I think we don't need this. I will admit, certainly, like, I'm still... what would we say? So, like, I have medium experience only in the core. I've done a lot more in the core than before over the last year or two. But still, certainly, like Dan and Scott have a lot more. So I believe, though, what this is talking about is kind of a, like, goes without saying sort of thing again. Like, it reads as helpful sort of to me if you don't know, but I think the deal is, like, people working in here know about the not being safe to call from certain places stuff. I think maybe it's not necessarily worth keeping the thing here. 0 on success, negative on error. Oh, negative error number on failure, and it never raises. That's nice. That's concise, so I'm fine with that. 0 on success is going to be largely the same. Negative NP rofs on an object with write enabled true. Other negative error number on failure never raises. False equals, so iOS control native. False equals operation not implemented. The caller turns that into none. Whether the object may write at all. The runtime half of the write gate. Yeah, so this is again talking about the write gate was in the original plan. It was like, we're not going to do writing because it is dangerous. And there was a compile flag, and then there was a runtime, like you have to pass the argument when you initialize it. Because also when this was done, we did not have auto mounting yet. I did writability before auto mounting, I believe. So when you auto mount, there's no runtime flag because there's no runtime. Like, you don't have to initialize it. It initializes itself internally, and it's writable to the host, not the CircuitPython. But you can, in your bootpy, you could swap it the other way, or CodePy, actually, I think, as well. Maybe. I think you could do it in either, but you would also need the settings toml thing to disable the auto mount of it, I believe. All right, board. So we're done with that module for now. I mean, it's alphabetical. We may go back into it, but this is board.c for it. Unlike normal CircuitPython, this one's entered from a bootloader that has already brought hardware up. It starts the 2 clocks, HF clock, LF clock. It leaves, I'm guessing maybe that's high frequency, low frequency. It leaves PWM 2.3 and SADC enabled. It also starts the watchdog that we cannot stop. The app has to take the machine over from a running state rather than a reset state, and it has to do so quickly. Yeah, I think this is a good comment to keep. This is all very true about this device. The deal is that for this device, first of all, it's using the bootloader that came on it. So this is not UF2 bootloader. This is not something that we control. Theoretically, if you wanted to be dangerous, if you wanted to live life dangerously, I think you could maybe overwrite the bootloader, but I am not going so far as to do that, I don't think. So I have been at the very least sticking with the stock bootloader, and the way it works is when the device first boots up, it's checking for these 2 buttons to be held in when it first boots up. Here, we can even just do it actually. Well, I'm going to turn it off by holding this button over here. That light will blink and it will disconnect from my computer. I'm going to unplug it. It actually turns itself back on when you unplug it. So I'm going to turn it off again. So I should have unplugged it first. There we go. Okay, so I turned it off. I think that was the off blink. It was not actually the off blink. I didn't hold long enough. That one? That one must have been the off blink then. Okay. probably can't do this to where you can see everything, but basically I hold those two buttons down, I plug this in at the same time. No, I think I did not actually get off. Ooh, we were off. Let's see. Okay, hold on. Okay, that should be off. Hold those two, plug this in. There we go. Okay, I didn't do it long enough. So you hold those outer two buttons while you plug it in. Plugging it in turns it on, which launches the bootloader. The bootloader checks for those two buttons to be held for, I think, maybe 2 seconds or something like that. And then if they are, it will launch you into the actual bootloader that lets you overwrite the application firmware. And then this light will stay on when you are in that bootloader. So this is the indication that you're in the bootloader. You can write to it. It stays open for like 60 seconds, I think, which is enough time to transfer a firmware pretty comfortably. And then you could also press the button to exit, and then that will launch CircuitPython. Or if you wait for the end of that 60 seconds, it will just automatically launch CircuitPython as well. So, and those buttons, so how this ties back to the PWMs and stuff here, those buttons are using a resistor ladder. So they are not just plain old digital in out, one button to one pin jobbies. Instead, there's like a single pin that reads a bunch of buttons, and there's a resistor ladder. So when the buttons are pressed, it makes a different resistance. It has to do an analog read and then match against a sort of known resistance value for each one. And then all of that stuff happens in the bootloader, which means by the time CircuitPython starts, all that stuff kind of remains in place, including the watchdog, which gets armed. Then on NRF, on Nordic, the watchdog cannot be disarmed. So once it's armed, it's going. So the bootloader arms it. We have no choice but to keep feeding it. Otherwise, the device will reset after, I think it's about 5 seconds, but I do have it set to 4 just to be safe in the core code. The MCC supervisor mount leaves the cards reset and rail alone while it's up. The header stubs auto mount to false when the auto mount is not built. Board reset pin default leaves the cards reset and rails alone while it's up. Header stubs auto mounted is auto mounted to false. Right. So if this is disabled by the build flag, then there is a stub that returns false for auto mounted. Because I guess something is going to try to call it. Yeah. Basically, something will try to call this, and if it didn't get defined, then it would fail. But it's usually defined. The real one would be defined somewhere guarded by this flag. You could go to all the spots where this is called, and you could guard them with the flag. That might just be the better option, truthfully. I think this one is another one. I'm going to leave it this way. I'm going to leave it with the comment because it does explain what it's for. But it would be interesting to check, like, how many places is that actually called? Would it make more sense to just wrap them in the if statements there instead of, they're not actually if statements, right? They're compile ifs. I forget what they're called technically. Template? I don't know. Anyway, whatever they are. Pins in this this file drives directly named here rather than repeated as the map, so that the quiescent configuration and power off sequence cannot drift apart. Okay, we don't need any of that. That's just extra pros about about this. But the pins, I think this is good. And then each pin is labeled, which is also good. Both LED rows active high. Pin LED heartbeat is the first track LED. So that is the same one that the bootloader uses. That's this one right here, which is why the REPL blinks it. That blink right there was the heartbeat that this thing is talking about right here. Which is also status and board off confirm. Yeah, we don't need any of this. This is all about why. Like at one point, it used a different LED. It used one of the side ones. There's LEDs over here as well. And at one point, it was using one of those as the like main one, and I told it to switch to the front, and it was like, let's switch to the front because it's much easier to see. And then it sprinkled that comment all over the place. Whether the first light heartbeat, yeah, we don't need that. So first light, it was talking about when we booted it the first time. Whether the first light heartbeat still owns this, cleared by board init, see board early init. Heartbeat lit. Timeout iterations. Bound wait for peripheral to acknowledge a stop. The events below are only specified to fire when the peripheral is actually doing something. And what the bootloader left running is exactly what we do not know, so this must never be an unbounded spin. On this device, the hang is a watchdog reset. Watchdog reset loop with no REPL. You'd have a couple of seconds of REPL, but yeah, it wouldn't be good. I think we really only just need this part. All of that, what it said is true, but it's not, I don't think that it adds much to the comment here specifically. But the gist of this is like, we need to feed the watchdog at least once every 4 seconds. And again, it's like maybe it's actually 5 or 6 seconds, but I did 4 to be safe. And if we don't, then the device will reset. So basically any spot where there's something that is doing whatever for more than 4 seconds, it had to have a bit inserted that's like, you know, if the watchdog is enabled, then feed it type thing. Read back to flush the right buffer per the errata guidance for clearing events. I think that's fine to keep. Board early init, first light. Maybe it actually, oh, you know what? It's not talking about first light as the, let me change that though. Heartbeat lit, first light. It's actually talking, I think it's actually talking about when it turns on. If I'm going to turn it off, it will blink right there to indicate that it turned off. It also disconnected from my computer. I heard the doodaloo. And then when I turn it on, this will be the one that blinks like that, which is a standard like CircuitPython thing. All the devices do that on an LED. I think that must be what it's talking about for the first light. Whether, so I'm actually going to call that the boot up blink heartbeat. I don't know if there's a precedent for, I'm not sure if it took first light from somewhere else or if it made that up. But it was also referring to first light as, I'm almost positive it was referring to the first time we flashed the device and it booted up successfully as first light. This device has no display. its only error surfaces the REPL, which doesn't exist yet, and if we failed bad enough, then it won't. The app dies before USB enumerates, or if the bootloader never jumped to us at all, both look identical from the host, nothing appears. One LED lit on the first instruction of the board separates them. Read it as never lights. The bootloader did not jump here, so, or we died in the reset. Lights and stays on. We're running, but we didn't reach board init. Suspect the file system formatter or something before the workflow starts. Okay, so if it was formatting like CircuitPy drive for the very, very first boot, it would stay on for an extra second or two or whatever while it formatted, it sounds like. Lights then goes out, board init reach, the boarded USB is next. So from here, the absence of TTY is a USB problem. Okay. These are helpful. These are like troubleshooting. This means this, that means that. First light, boot up, blink, status, boot up status blink. Is it telling its status ultimately? One LED. And we just don't need this. The first light, boot up status blink. And then here's your troubleshooting table. Nothing is initialized yet, so this is a raw GPIO write rather than anything SAS LEDs. Okay, I don't think we need any of this. No interrupt we might take here as handler and enabled pending RQ. CircuitPython enables what it needs afterwards. Similar, I don't know that we really need all of this. Break any PPI wiring before stopping the peripheral, so nothing we stop can be restarted by a leftover event task connection. This one is more about an actual reality of what it's doing. This one up here was more about like these things haven't been done, so here's why we didn't, or why we did this part. But it is talking about things that haven't been done more than this one, which is saying specifically what is happening and then why. Not what didn't happen yet. The bootloader drives the LEDs with PWM 2 and 3. 0 and 1 are stopped too, so the PWM starts from a known state no matter whatever the bootloader did. Okay. I think just end it there. Bootloader reads the button ladders with SAADC. It leaves enabled. One matters, so here's another claudism. This one matters beyond tidiness. Port init calls analog init, which triggers calibration and spins until calibrate done. ADC stays busy with the bootloader's easy DMA conversion would... And ADC still busy with the bootloader's easy DMA conversion would never produce that event. I think what we do is the bootloader reads the button ladders with ADC and leaves it enabled. He'll clear it here. Correct here. Maybe even just so clear it. Because this is basically resetting all the ADC states. Pins that must not float. Reapplied after every reset all pins. Startup at, which is at the startup and after each VM run. I don't think we will need this. This is another one of those, like, is nice if you're brand new, but also is not really necessary, I think, for most of the people looking through the code. Pins that must not float. Reapplied after this. None of these are marked never reset. The Python can still claim them. Codec driver has to be able to release task reset, and audio has to be able to raise enable pin. The point is only that the resting state between runs is a defined state one. Python. Done so that the resting state between runs is a defined safe one. 3072 millihertz oscillator enable held low. We are in board here, so yeah, so this is specific to the board. Oscillator enable held low, draws current straight through system off, so a floating pin here would flat. I think we could just stop with this. Or a floating pin here would drain battery. Codecs and the Bluetooth module held in reset, all active low, so that nothing downstream of us starts making noise or driving a shared bus on its own. These pins, NFC pins. NFC, like near field communication? Is there an NFC thing? Maybe that's not NFC. Maybe that's a different NFC. Okay, so here's one of these things. This board deliberately does not build with config NFC-T pins as GPIOs because that option writes UICR. Instead, it relies on the bootloader, I think this means, having already cleared NFC pins protect. Their firmware drives these same two reset lines. If that turns out to be wrong, these two writes are simply ignored by the hardware, and the symptom is speaker amp and Bluetooth module that never come out of reset. Read the actual pins at first line. Okay, so we've already done this, and this succeeded. So I don't think we need to keep the, like, if this, then that succeeded type stuff. The UCIR thing here I'm going to keep for the moment because these are some of the things I need to go back and like try to figure out whether, like, how dangerous these are exactly. So as I understand it, UICR, this is like a configuration register in the NRF 52840, and basically in the plan that I was working from for adding support for this SP-1 device as a safety measure, basically I have got it all set up to where we will never write this register out of an abundance of caution, because there's some chance if we were to write this register with certain configuration values, because of the way this board is, how it doesn't really have a reset button that you can get to. It doesn't really have a way to pull the power that you can get to, right? Like you have to, the firmware has to be running and healthy and listening for this button press in order for the device to be able to turn off. And the only way to enter the bootloader is from a device that is turned off. So if you're ever like, if you ever get to a state where you can't turn off, then you can't get to the bootloader either, and you basically just have to wait for the battery to die. And so there's a few places where CircuitPython was doing this UICR writing thing, but they are kind of like removed in this build. But I need to go back and see, like, is that actually super really necessary or not? I'm not sure. It may be the case that it was, again, an abundance of caution, but not actually technically necessary. 1 second, I'm going to do this for just a second here. And we're back. Okay. UMC held and reset with the VCCQ rail off. The albums live on the chip itself and are unaffected. This only keeps the rail from floating. Unless supervisor has the card mounted, then this is the one exception to the paragraph above. I think, honestly, we don't need any of this, truthfully. I think the code kind of explains already that it's keyed on the auto mount or not. The rail feeding the faders and both button ladders off unless something is actually reading them. Let's see, what was that? Maybe we actually do this. Yeah, I think actually we keep that part. Off unless something actually needing them. Actually reading them. Both LED rows. Off. Except the first light. Heartbeat status blink. It actually blinks in the REPL too, though, so I don't know why. Except the first light, heartbeat status blink if it's still running. Main calls reset all pins immediately after port init, so without this, the heartbeat would last microseconds and show nothing. Okay. This just gives it time to actually blink and be visible, it looks like. The function button, so this is the one here that turns it on and off. It's the only GPIO button, so this one is the one button that doesn't use the analog resistor ladder trick. This one actually does have a single pin that just goes high or low or whatever when you press it. Active low, and the only wake source out of system off. Keep it readable at all times. The supervisor's power off gesture depends on it. Maybe that should be, it's kind of part of the same one, I don't know. I don't actually really understand M dash. I barely, if I'm honest, understand comma usage correctly. So M dash usage is a little beyond me. I try to not use them so that I don't misuse them. Misuse commas enough as is. I don't need to misuse both. BQ2, what is that one? That is the battery charger. Charge enable, active low, drive it low, so a plugged-in device actually charges. The current set pin P10 is deliberately left alone since the resistor configuration it selects not been established. I should make a note to try to establish that then. Board.c. Try to establish resistor config for you. Enable. I mean, maybe it won't matter. I'll at least ask the agent about it. It may not matter though, honestly. It's definitely charging. Like right now the battery is full because it's been plugged in a lot while I've been developing, and it's been on CircuitPython for multiple days at this point. And I've had it plugged in like all day long to where if it was not charging, it would not be full. So I do believe the charging is working. In which case, maybe the real thing to do here is just clean up the comment. Called once at startup, so this could maybe say and or clean up comment if not relevant. Called once at startup, says boarded after the file system is mounted immediately for your workflow. The last board specific thing that happens for enumeration, which makes it the right place to end the heartbeat. Muting the codecs on the way out. Dropping the reset line and the oscillator is enough to make the board quiet and save the battery, but it cuts both codecs off mid-signal. This is the main audio codec, loses its clock, and the this is the amp for the speaker. Loses its reset with whatever was on the output still on it. The loopers shut down. Looper is a different firmware. This is a different third-party firmware. Bit banged rather than driven through TWIM. The gesture fires from power off tick on a VM backward branch, so a bus IO transfer cannot be in flight, but the peripherals configuration is still whatever the last owner left. Possibly nothing at all, if no Python code ever got the I2C bus. Bit banging has no state to inherit, needs no easy DMA buffer, and is trivially bounded, which matters on the path with no REPL to recover through. 10 bytes at okay, this whole thing is basically justification for bit banged rather than TWM. I'm not sure it's really necessary. Open drain, input buffer connected, so ACK and clock stretching are readable. The internal pull-up is bell and braces next to the board's own. I don't know what this phrase means. I'll just pop up somewhere else. Using 2 or more extra safety steps to prevent a problem. Belt and braces, I see. Remove to get an I2C release so nothing pulls current and system off. I'm not gonna keep belt and braces because I don't know how commonly familiar people are with that. The internal pull-up is additional safety next to the board's own. It's removed again by release, so nothing pulls current system off. I2C claim. Whatever owned these pins through TWIM keeps driving them. We are about at time here, so if anyone has questions, comments, or anything else, now's the time to drop those. I'm going to do this one real fast here, and then I'll probably wrap up after that. Do remember also Friday CircuitPython day. I'll be streaming Friday afternoon, evening. Let me pull up the thing on that, actually. I think it's 6 p.m. Eastern, but I do want to be sure. I think 6 p.m. Eastern, Game Jam live stream. We'll be doing some Pico game. You want the little bit of a spoiler precursor to that, you can check out my stream over on my channel from this past Saturday. I started looking around a bit and trying to figure out what game I'm going to build. So Friday evening, 6 p.m. Central, I'll be back to do that. And then I'll be back next week as well on Tuesday at the normal time. Whatever claimed these pins through TWM keeps driving them while the peripheral is enabled. Pin CNF notwithstanding. TWIM 1 and 0 share their base address with SPY, both disabled. On the power off path, yeah, Blinka, CircuitPython day. On the power off path, nothing after this returns to user code, so that's free on the soft reset path, reset board. We don't need to know which part of when it was added. In fact, this could just be commas instead of parentheticals, I think. The board does come back and it's still free because bus.io cannot survive that reset. The board buses and reset port have already run by then, and the next, I think we could just end this here, all of this. All of that is like justification for the prior sentence, or the reasons why the prior sentence is true. Okay, yeah, and then I will stop here and wrap it up. But that's what I'm doing. We're, I don't know, about a third or so through. I think some of these changes are not as exhaustive as others. I believe, I haven't profiled the code, but I think the EMMC is like the majority of the code, and I've got through bindings and block dev. There's a few other files to do a bit later on, but I think most of the new code is that. A lot of the rest of the code is like, if soft device enabled, then do a thing instead of just do it unconditionally. But all right, that's gonna do it for my stream today. Again, check back later today, 4 p.m. Eastern, 1 p.m. Pacific. You will find streaming right here where you are watching me. Instead, you will find JP with a wonderful product pick of the week, where you can get a great discount on whatever the product of the week may be. And as always, if you purchase from Adafruit, you're helping support the open source development that they support by paying people like me. So huge thank you for that. And I think that's it. That's all for today. I will see you all on Friday for the Game Jam stream. Hope you all have a wonderful rest of your week and enjoy CircuitPython day later on this week. And I'll see you next time.